Okay, we're going to be looking at module number 8, which is mechanism design. We're going to kind of like go backwards a little bit in the book to chapter 5, and you're going to find the learning plan for module number 8 here, in this module, and it's going to be chapter 5. Chapter 5 starts on page 109, and I'm going to click on, actually I'll download it and I'll pull it up, the PowerPoint presentation for this particular chapter. So I'm just gonna kind of run down here. I do have my book open. I have it underneath my camera, so we'll be kind of referencing that as we go. So our first slide here, I want you to just take a minute. We've been looking at 4-bar mechanisms and slider crank mechanisms, and we've been all the way along kind of identifying different types of applications of these mechanisms in the real world, if you would. So I just want you to take a minute and try to list as many applications as you can think of for a 4-bar mechanism and like a slider crank mechanism. So kind of in their real world setting. Think of and make a list of applications of 4-bar and slider crank mechanisms. I'll time you 1 minute. 1 minute will take. Make a list. Unless you can't think of any. I know it's Friday. It's late. I just had kind of funny that today we had a day-long meeting that I had to attend, and I kind of felt like that whole I just don't even have the energy anymore. All right, we're gonna go another slide. So you've got your list that you thought of in your mind, right? Our next one is now take 1 more minute. Let's do a Google search really quick and find some applications of 4-bar mechanisms and slider crank mechanisms to add to that, maybe that mental list that you created. So just a couple of quick ones. It's not often your teacher says, get out your phone and go on Google and do a search. So now, let's take a quick, we'll call it a whip around. And just think of, if you want to share one mechanism that you either found or thought of that you don't think anybody else thought of, okay, that you think is unique. So, so we'll start online for those who are there. And you can put it in the chat, or you can verbally say it. Okay, BJ said a windshield wiper linkage. Did anybody else think of that one? Maybe not. Good one. All right. What else? Anybody else online have anything that they want to add? Something from your list? Oh, the brushes on a car wash. Yeah, absolutely. Yeah. An ironing board. Good one. Wow, Logan. Great job. I didn't even think of that. I do the ironing in my house. Awesome. Other applications, we'll just kind of randomly say now. A scissor lift, absolutely. A piston. Yep, a piston that is going to be in a bore, a cylinder bore, right? Engine, absolutely. Yep, that's classic. So any other ones that we didn't hear? Okay. All right. Then I know this is one more step here, but I want you to pick one of those things that were on your list and take 1 last minute to think of all the variables or the constraints or the considerations that you need to think of as you're designing that. Okay, so for the windshield wiper application, I mean, what are the things that you need to consider as you're just kind of laying it out, you're designing it, you're figuring out, getting it to its final form. What are things? So kind of make a list of what you have to kind of think of. Range of motion, absolutely. Yep. So like the stroke, or in the case of a windshield wiper, because it's going through an angle, we call that the throw angle. Like, what is the total throw? Yeah, what else?
what to make it of.
The materials, absolutely. Now that might not be a kinematic part of the design, but you're thinking about that early on for sure. Yes. What else?
It's form and factor in terms of size.
Say that one more time.
It's form and factor in terms of size.
Yes, it's size, absolutely. Yeah, because the windshield wiper, using that example on a Mack truck, is going to be different size-wise than, I don't know, on a little Beetle. Yeah, absolutely. Yeah. Other considerations.
Speed.
Absolutely. Speed, acceleration. Yep. Anything else that you can think of?
Efficiency.
Efficiency, sure. Cost, always. That's what it comes down to. What was that? Manufacturability. Yes, you need that always in the back of your mind. Yes. How complicated or simple it could maybe be made, right? Yep. We're gonna see that a little bit later. What was that?
Wear parts.
Yes, serviceability or wear items that you know, over time, you're going to anticipate probably having to change out just because, right? Others, good list. All right. Well, you know, as we're kind of getting to the end of kinematics here, we know that kinematics has been the study of motion without regard really to any forces, which is kind of odd. You guys had statics, and then you kind of are not thinking about statics anymore, but you know that you have to think about them. And so so kinematics is really that kind of layout side of things, but that doesn't mean that you're not thinking about some of those other things like we just talked about, the materials, the wearability, the cost, the functionality, the manufacturability. Those are all going to be affecting how things are going to be made. Okay, so that's good. In this chapter, I don't think I went too far ahead. In this chapter, we're going to get to learn about how we use graphical methods. We're going to use AutoCAD to initiate the design of a mechanism. And so we're going to keep it in that simplified kinematic form. But now, instead of going from the perspective of draw the kinematic diagram for this that has these dimensions, you're going to really be given, what is that final, you know, stroke? What is that final throw that we need? What is the time that we need to do it in? And now you're going to kind of start at that end product and then go backwards to figure out, okay, what is the length of my crank? What is the length of my connecting rod? And that kind of thing. So you're going to be laying it out graphically to get it designed. So kind of going in the opposite direction from what we have been used to. You're going to find out why this is important, and then find out the techniques and the processes to get there. And then lastly, this also is going to be part of thinking about, now I'm not going to make you, you know, decide what you're going to do for your capstone, but these portions are going to be potentially, you might have a capstone product or a project in mind that some of these things that we learned in kinematics are going to apply for, especially in those early stages of that design process and the layout of, okay? All right, so objectives here are going to be, we're going to be looking at and describing mechanism synthesis. All right, design an inline slider crank mechanism, know the desired mechanism time ratio, and then use timing charts to synchronize the motion, as well as use graphical methods to design the various mechanisms as well. And it's really kind of a backwards process. So it won't be unfamiliar, but it just hasn't been something that we've done to this point yet intentionally. So in section 5.1, this is our introduction. They talk about synthesis, and synthesis is the process of designing a mechanism that's going to produce a desired output motion for a given input motion. And so it's kind of like you're given, I'm not going to say few variables, but all you're given is this is what we need in the end, and now you get to design it. Okay. Now, additionally, there's probably usually a couple more constraints, namely space is usually going to be something that you have to fit your design within. But other than that, you have the freedom to decide how you're actually going to accomplish that. Now, the specific type synthesis is going to be once we know the motion that we need, whether it's linear or if it's oscillating, now all of a sudden we're able to pick the type actual mechanism that we're going to be using. I'm just going to look here. Okay. If I couldn't remember if I started the recording or not. I'm like, oh crap. I hope I did. I did. And the important part here, you're going to notice I have a note there to keep it simple with an exclamation point. Believe it or not, it sounds simple, but it's not always simple to do. Okay. Meaning trying to minimize your parts, or maybe combining a couple parts so you have fewer parts than what's there. Keeping it simple. It's actually easier to make something super complex than to kind of back off and try to eliminate things that you may not need. So, so thinking from that side of really thinking about each and every part, each and every piece of that motion, if it's actually needed. And then finally, we're really going to focus a lot on dimensional synthesis, determining what those lengths are of each one of those links. Okay. Once we determine our final motion. So that's that. Now, time ratio. There are two distinct types of motion. One is synchronous motion, or I'm sorry, symmetrical motion, and the other one is non-symmetrical. Symmetrical motion is exactly what it sounds like. It means that whatever the outward stroke is, for instance, on a piston or on a crank slider mechanism, the outward stroke is going to be exactly the same amount as the inward stroke, but timing wise as well. So it's going to be the same time interval in and out and in and out. And so we say that that's kinematically balanced. And you also have the opportunity, because it's the same timing in and out. Most often those types of applications are, you're going to be doing work on the outbound stroke, but then also back on the return stroke. Okay. And so you can do work on both sides. And engine mechanisms, windshield wiper mechanism, those are going to be examples of symmetrical motion applications. So I am going to click my little link here. There we go. It should take us to this video. This is a kind of a nice little video. This is synchronous, or I say synchronous. It's a symmetrical motion. So you're going to notice it's a slider crank. And as we go out and we come back the other way on our return, the timing of that motion is exactly the same. So we would have an opportunity to do work in both directions. Okay. Now, the other thing, if they flip this back again, I don't know if it's easy to see, but the center of rotation of that crank is in line with the actual travel of that slider as well. So this would be an inline slider crank mechanism. All right. Okay. So that's an example of that, which I'm sure we all kind of had pictured, but we've only really looked at pictures as opposed to kind of seeing that motion. Now, the other type, as I mentioned, is non-symmetrical motion. And non-symmetrical motion is where that speed on our outward bound part of the stroke, for instance, on a slider crank mechanism, is not the same as the return stroke. And most often then you are only doing work in one direction because of that. And usually it's going to be the slower stroke side. And then you have a quick return, and then you do work again back on the outward, but then you have a quick return. So, so cutting machines or package moving devices, once they move it, that's the work that they needed to do. They can come back and they can kind of go kind of fast on the return, and then they can move and then come back fast on the return. Cutting machines as well, in that one direction is where they're doing the work, and then you can return quickly. So here is an example of one of those. Now, this isn't super pronounced, but you'll notice that slower on the outward, which is this one, and then fast back. So the work would be done in that to the left side of the stroke, and then the return is going to be on the opposite side. And sometimes these can get like super fast on the return, because as you can imagine, right, time is money. So the faster you can get it back to its original position where you're not doing work, the better you are. Okay. All right. So that's each one of those. Oopsie. Let's move forward. So now, as you can imagine, when we start trying to relate these different elements, there's going to be equations that we have to do. So starting on page 109, that first page of our chapter, and in the second column, the equations that are going to relate some of these things are as follows. Number one, time ratio. Okay, time ratio Q. When it's something other than one, that means that we are a non-symmetrical motion. So if I look underneath, what I'm going to encourage you to do is, and I'm going to actually do it as we hit each one of these equations. I'm going to kind of, so I don't have to go back and page. I know there's not a lot of pages in this chapter, but it's not a bad idea to start an equation sheet here so that when we do our homework, especially, we've got everything in, a nice spot. So we're going to start by putting in our time ratio. Now our time ratio Q is going to be the time of the slower side of the stroke, okay, divided by the quicker, all right? So we're going to say Q is equal to, and it's going to be referred to as, just let me double check this really quickly. I'm pretty sure it's T1 and T2. Yes. So T1 is going to be the slower side of the stroke divided by T2. Okay, so I wrote mine like this. So T1 divided by T2, and it's going to be the lowercase t's are going to be the times of those individual outbound and then return parts of our stroke. And this is going to be greater than or equal to 1. Okay, greater than or equal to 1. So now, as you can imagine, when it is equal to 1, okay, when I should put Q is equal to 1, sorry. When Q is equal to 1, that means that we're in a symmetrical motion situation, meaning that the outward stroke and the return stroke are exactly the same, okay? When it's not, or when it's greater than 1, that means that we've got that quick return type of a situation where we don't have the same time on both sides. All right. Now, the next one we want to look at is called the imbalance angle. Okay, the imbalance angle. Now, the imbalance angle is only going to be evident when we don't have an inline crank situation. Okay, an inline crank situation. So I'm going to peek forward here to our diagram. Now, on an inline situation, we know that when our crank is in line with the motion of our piston in this case, or our slider, when these are laid out in their extreme position, so all the way out and all the way in, these are in line with one another. So there is no angle between those two. Okay, but when we have an offset slider crank mechanism where there is an actual distance between the angle, or I'm sorry, the center of rotation of our crank and the path that slider is going to take, we have this L1 distance. Now we do have what we call an imbalance angle. So when we're on our extreme position all the way out and our extreme position all the way in, do you see how there's an angle here between? That's called the imbalance angle, because now they're no longer in line with one another. Okay, and those only occur when we have an offset slider crank mechanism. Okay, and we're also going to find out that that's only going to occur when we have a Q that is greater than 1. So when we're in that quick return situation. So an offset slider crank mechanism is a quick return type of a mechanism where the inline is going to be the symmetrical. Okay, so there would not be an imbalance angle here, or they call it beta. Okay, so let's put the second two equations then relating that time ratio with our imbalance angle. So depending on the information you have, we can find the time ratio using betas, and we can find beta using the time ratio. So it's just really each one of those. So we're going to write down those. And again, depending on the information that we have and what we're trying to get, will then let us know which one of these we're going to be interested in. And it is equal to 180 degrees. So not terribly complex or hard equations, but just kind of understanding and knowing, you know, what they mean. Okay. All right, let's get back to our PowerPoint. Oh, no, I'm going to stick here. I'm going to turn the page, and at the top of the page, we've got a couple more to add to our equation sheet. So the next one that we have here is going to be the calculation for the total time for a cycle. Okay, so that's going to be referred to as change in T for the cycle time. So change in T cycle time is going to be equal to T1, which is the time of the slower stroke, plus T2, which is the time of the quicker stroke or the return stroke. Okay. So you're going to notice that we just do it that way. Now, a cycle is going to be one revolution of our crank. Okay. Just like it was for a cam, one revolution. Like, what do we have to accomplish in one revolution of our crank? What motion needs to occur? And we're going to divide that into that, you know, looking at the stroke. And then the last equation that we have here, I'm not crazy about how they show it, so I'm going to write it a little bit different. This is going to be the angular velocity of our crank is going to be equal to, okay? It's going to make more sense, I think, when I write it out. Not saying it's better, but it kind of is. Okay. It's going to be one revolution divided by the time of one cycle. Okay. Or one revolution of your crank. Okay. So the angular velocity of the crank. So how, you know, we want to go around in one revolution. How much time does it take to do that? And they write it. It is a reciprocal, yes, but you're really looking at revolutions per whatever amount of time that you're looking at. So that's why I write it like this, because it is a revolution on top. Okay. All right. So the first example that we're going to be looking at here is going to kind of be using all you know, 3, 4 of these variables. So it says that we have a quick return mechanism is to be designed where the outward stroke must consume 1.2 seconds. Okay. And the return stroke needs to be 0.8. So that means the slower of the two is called T1 and the quicker of the two is going to be called T2. Okay. They want us to determine the time ratio, which is Q, the imbalance angle, beta, the total cycle time, and then the speed of that crank. That's going to be our W. Okay. So what we'll do now, I know it's written out here, but as you know, I like to kind of go through this. I think it's more meaningful when we kind of take this step by step and devise, you know, our plan. So starting off here, this is example 5.1. And what we're given, okay, what we're given is going to be our T1, okay, which is 1.2 seconds. We know T2, which is that quick return, is 0.8 seconds. And I think that's it. That's all they gave us, right? Okay. So we've got to calculate those other items. So, so we need to find then, doesn't hurt to add that. We need to find Q, beta, change in T, and W of our crank, or angular velocity of our crank. Okay. So using our equation sheet, if we only know our time, what do you think the very first thing is that or maybe there's multiples that we could figure out? What do you think is the first thing? So we've got Q, change in time, beta, and W. So we could do Q, right? Q just needs T1 and T2. So we can figure out Q. What's the other one that we can actually figure out right away too? The cycle time as well. Yep, right here. Okay. So those are the two that we'll do. So step number 1, then we're going to say Q is equal to. So again, make sure that you write out your equations in variable form first, and then input your values with the units. Okay. So that we can kind of see what's either canceling and or combining. So my T1 in this case is 1.2 seconds. My T2 is 0.8 seconds. So my Q, I'm going to get my seconds canceling out. It's going to be 1.2 divided by 0.8. Do you get 1.5? Okay, and it's just a ratio, so there are no units in this case, right? Okay, cool. So we can put a box around that, and we can say we got Q done. So we can say check. All right, and then we already saw that we can do our total cycle time, so we might as well do that one right away. It doesn't have to be in order. So change in T, which is our cycle time, right? It's going to be T1 plus T2. So that's pretty easy. 1.2 seconds plus 0.8 seconds. Looks like our change in T is going to be equal to 2 seconds, right? There we go. Done. That one's done as well. All right, we have beta, and we have our angular velocity of our crank. So really doesn't matter which one we do first, because for beta, we have Q, right? And then for W, we have our change in T. So which one do we want to do first? You tell me. Beta or angular velocity of our crank? Let's do beta. Yep, let's do beta. So we're going to write out beta's equation. So step number 3 here. Beta is equal to 180 degrees. Q plus 1. And Q minus 1. So that's going to be multiplied by. So 180 degrees. And our Q was 1.5 plus 1 on top, divided by 1.5 minus 1 on the bottom.
Isn't it minus
Did I do that wrong?
1? Yeah, I think it's minus 1 on the top, plus 1 on the bottom.
You are correct. Yep. Thank you. Thank you. So, yep, we need the right equation to have a chance at having the right answer, right? Okay. So our beta I think that's the right answer if I remember right. Yep, 36 degrees you should get. Okay. And then any questions on that so far? All right, so then our fourth step then, so we've got beta done, then our fourth step is going to be our angular velocity of our crank. And if we come back over here, it's going to be 1 revolution divided by that total cycle time. So number 4, change in T, it's going to be 1 revolution divided by change in, oh shoot, it's W. Oh my goodness, I'm not, maybe we should have had a work day tonight. Now we need to get this done. This is good. 1 revolution divided by 2 seconds, right? So it looks like that's going to be 0.5 revolutions per second. Okay. Now, as you know, the preferred units for angular velocity are going to be RPMs. So we just want to do a quick conversion to RPMs for our final answer. So we know that there's 60 seconds in 1 minute. So the seconds cancel out here. So our W of our crank looks like it's going to be 30, right? 30 RPM. There you go. And that's the final part of that. Okay. Any questions about that? I think the first 2 homework problems are going to be kind of using those equations and solving in a couple different ways those same variables. Okay. So, so those will come up again. All right. Now, as we look at this, notice that our Q value was greater than 1. Okay. This means that we are in that non-symmetrical, and it did even say that there was a quick return, and it makes sense because we had less time on our return stroke, the T2, than we did on the outward stroke. Additionally, we have a beta angle. Now, for instance, if you would try to calculate the beta angle for a symmetrical, meaning it was an inline, you would get 180, right? Because you'll notice that my Q Oh, you would. Yes, you would. Yeah. Even though they're in line, you're correct. 180 would be, yeah, the other way. So it would be 0 divided by 0 times 0, right? No, it would be, if this is 1, it would be 0 divided by 2, which is 0, because anything division by 0 is infinity, right? Yeah. So it would be 0 times 180 is 0. So your beta will come out to be 0. You're correct, not 180. So it just means that there's only going to be that imbalance angle when you have a quick return, which in the case of a slider crank mechanism would be an offset rather than an inline. Okay. All right. Let's get back to our PowerPoint and catch ourselves up. Oopsie, not one. It's this one. There we go. No, not that one. Did I lose it? Oh, here it is. I have it under, that's right. I opened it in the PowerPoint. All right. So we did our equations. We did our practice problem. Now we're going to start looking at designing slider crank mechanisms. So slider crank mechanism is going to provide that reciprocating linear sliding motion of whatever it is our output motion needs to be. So classic examples, and this came up when we did our kind of our brainstorm, if you would. An engine, right? Those pistons are going to move a precise distance. That's what we call the stroke, as that crank continuously rotates around. So we'll look at a really quick example here. So here you'll notice the crank going around, and then the piston is going up and down within the confines of the bore of that cylinder in a linear fashion. Okay. The next one that we have is going to be sewing machine, power hacksaws, and compressors. And I forget which one this is. I think this might be a power hacksaw, if I remember correctly. Oops.
There's one simple hearing hack anyone can use to improve their hearing almost.
You love.
Did you?
Very happy, kind of like, I don't know, Mr. Rogers' Neighborhood or something. Oh, look at, he's in the corner. There we go. I know. You're going to be hearing that in your sleep tonight. So, oh, it can be happy. It can be fun. All right. So, so inline crank slider. So if we look at our illustration, it looks like figure 5.3 up on the top of page 114. There we go. They're referring to this illustration here. So just to kind of point out a couple things. First and foremost, we've got our crank, which would rotate all the way around. And then you'll notice that it's drawn, we have two positions, one for the extreme outward position and one for the extreme inward position. And then just kind of an in-between location here. But this would be our extreme outbound, inbound. And then the difference between those two, that total displacement would be called the stroke. Okay. And then you can see here, these should look familiar to us. Those are going to be those lengths of each one of those links. And yeah, so that's the stroke of an inline slider crank. So let's look at determining the appropriate lengths for an inline slider crank mechanism. So first and foremost, when we go through this process, we always know what our final output motion is going to be. And most namely on a slider crank mechanism, it's going to be our stroke. So our stroke is going to be 2 times the length of our crank. And it's going to be exactly that. So if we go back to underneath here, when this is laid out all the way, right? Our stroke, our outward most extreme position to the right here is going to be out here. So then when we go around and this is in line now, that means that that's going to be the position that we're our furthest in. So the difference between those two is literally half of what that, I'm sorry. The stroke is going to be 2 times, or the length of link number 2 is going to be 1/2 its radius of whatever that total stroke is going to be. Okay, always. So if we know our stroke is 20 millimeters, our crank has to be 10 millimeters long. Done. Okay, so so that's like a known relationship for inline slider crank mechanisms. So that's what we see right here, and that's equation 5.8 in your book. Now, we're going to find that some of these relationships are going to be specific now to different types of actual mechanisms. So the slider crank, when we know it's stroke and it's an inline type of an arrangement, then our stroke is going to be half of whatever, I'm sorry, our stroke is going to be 2 times whatever our crank is, or our crank is going to be 2 times our stroke. So if you want to add that to your equation sheet, you can do that. That's a good one to have, because again, it's kind of a it's a rule of when we do our design for these. So go like this. So this is going to be an inline slider crank, and we know that L2 is going to be equal to our stroke divided by 2, right? Stroke divided by 2. So if it's in inches or if it's in millimeters, those units would dictate. Now, another thing, and this is a rule of thumb, our connecting rod, which is going to be our the length of our member number 3. So if we're using that conventional kinematic diagram numbering, number 1 is going to be our frame. Number 2 is going to be the crank. Number 3 will be the connecting rod, and number 4 will be the slider. So L3, referring to the connecting rod, it doesn't affect the stroke. Okay, so there is no effect on the stroke, but as a rule of thumb, you want your connecting rod to be at least 3 times greater or longer than what your crank is. Okay, or longer. Okay, at least 3 times greater. So underneath here, we're going to say L3 needs to be equal to or greater than, other way, or greater than L2 times 3, right? Or 3L2, yeah. There we go. And again, that's a rule of thumb. It's not, it's not that you have to do that, but it also minimizes the accelerations that can occur. And that's going to become more important when you look at dynamics. And that's going to be next semester, where you're now going to be introducing with the acceleration forces. Okay. And you have to deal with those forces. And once they kind of get going, sometimes they're not very fun to deal with. So you want to try to minimize accelerations. And this is one way that you can do that, by keeping that length of that connecting rod equal to or greater than 3. Okay. Now, sometimes it's not possible, so you just have to deal with it, but that's going to be something that you try to do. So the offset slider crank mechanism. So offset slider crank mechanisms are going to have now a distance between the center of that crank and the path that the slider is going to take. Okay. So if we look at figure 5, it should be 5.5, not 5.35, sorry. And this is going to be in the first column on page 115. Okay. This is an offset slider crank mechanism. So the offset is going to be this L1, and that's between the path of that slider and the center of our crank. So they're not in line anymore, okay? Now, these are going to be where we are going to see some quick return applications, okay? And it's that unbalanced motion, meaning we're not going to have that same time back and forth like we do with an inline slider crank. So depending on what type of motion you're looking at, we already have kind of two distinguishing factors. Do we want to have the motion the same time in both directions so we potentially could do work in both directions? Or are we more interested in the fact that we're going to do just our work in one direction and we need a quick return on the other? Now we're going to pick one or the other, and the quick return would be the offset slider crank. Now, as we look at the offset slider crank mechanism, determining those lengths of those two links, the crank and the L3 or the connecting rod. So first of all, the stroke is actually going to be greater than 2 times the length of that crank. Okay, so it's going to be something, the crank is going to be something else. And the range of the offset distance, and that's going to be L1, like how much can that be? That has to be less than whatever you decide your length of number 3 is minus the length of number 2. Okay, so it has to be less than that. So that equation is there as well. So if we take a peek underneath, and we look at some of these distances. Now, these equations are going to come into play, or these relationships are going to come into play when you lay out and you actually determine some of these values. So our L2 here, and this is again is going to be for our offset slider crank mechanism, we'll calculate that to be equal to 1/2 times AC. So what they're referring to is A is going to be the center of the crank rotation, and then C2 is going to be the distance all the way out to its outermost point on its stroke. So AC2 is the length of this line right here, okay? Minus A to C1, which is going to be the position of our slider in its inwardmost position, okay? So from there to there, and then multiplying AC2 minus AC1 times 1/2 is going to be then the length of our crank. Okay, so this would be for an offset slider crank mechanism. So if we want to add these, so this is going to be offset slider crank. Our L2 is going to be equal to, and this is going to be 1/2 AC2 minus AC1. And I'm going to just refer to equation 5.10 so that if you need to go back, you can. You'll also notice that we have L3 is going to be equal to AC1 plus L2. So let's look at that. So L3, let's see here. So L3 is going to be from here to the outermost position, and then it's going to be adding L2, which is the length of the crank. Okay, so L3 is going to be equal to AC1 plus that L2. So it's this whole distance right there. So we can add that here as well. So L3 is equal to AC1 plus L2. Oopsie. And this is equation 5, I think it was 11. And both of these refer to figure 5.5. Now, the procedure to graphically go through the process of designing or synthesizing the slider crank mechanism is as we see here. So the first thing you need to do is you need to locate the axis of the pin joint on the sliding link. Okay. So as we look through here, you need to, let me just peek back here for a second. If they're referring to, I think they're referring to either one. Yeah. So, so what we need to do is the first thing that's going to be identified is what is your stroke? And that'll be given to us in our problem. So whether we're an inline, okay, or we're an offset, we have to first determine, okay, where is that stroke going to be? Okay. Then we're going to, based on the motion that's desired, are we going to be an offset or an inline? Okay. And then depending on spatial relationships. Now, in the problems that you're going to do for the homework, there's going to be 3 of them that you're going to do. You're going to do an inline slider crank, an offset slider crank, and then you're also going to do a crank rocker. And there are some assumptions that you get to make as the designer. They're not giving you any spatial relationships that you have to fit within. They're only going to give you the final motion. So like the stroke or what the throw is going to be. And then you get to kind of pick the other numbers out of the air. And it's going to feel a little funny because up until this point, you've had like problems that you're going to be using. But some of these things, like for instance, on our slider crank, when it's inline, we can calculate our L2 based on the stroke, but then our L3 becomes, just pull it out of the air using the guidelines. And our only guideline for L3 on an inline slider crank is going to be that it has to be at least 3 times greater than whatever our L2 was. So if our L2 was 1 inch, you could be 3, 4, 5 inches and it wouldn't be wrong. Okay. That's where you as the designer, you're going to notice that in the answer key or in the back of the book, it's going to vary. They're not going to be able to give you, really a concrete number because it just means that you have to make sure that you're within the guidelines that are given. Okay. And that's what I check when I check your work. So if you're comparing to somebody else, you may not have a wrong design, but it just has to meet the requirements. Then when we get to the offset slider crank mechanism, here you start with your stroke and then you start looking at, all right, what do I think I need my lengths of my links to be about? And then that determines what your offset is. And then you start kind of filling in the blanks backwards. It's not quite as concrete as the inline. Okay. And then what you'll do is you'll figure out what your L2 is once you lay it out. And then you'll figure out your L3 based on your L2. Okay. All right. Just up.
Is it L1 be like first thing that you figure out?
Yes. Yeah. Yeah. On an offset, your L1, you want to kind of nail that down. Yeah. And it's going to be based on an estimate first. And remember, there is a range. I think it's, what does it say? Your L1.
Plus L5.
Correct. Yeah. Yeah. And sometimes you might assign it and then make sure that you check it afterwards once you get those nailed down. Mm-hmm. So it's not always a straight line process design. Okay. And you might, sometimes you just got to go with something first, see how it works out, and then back up and make adjustments as needed. Mm-hmm. Very common to do. So the next one is going to be design of a crank rocker mechanism. So a crank rocker mechanism is where we now are going to have that crank is going to be going around. So our L2, if you would, is going to be going around continuously. But then we have our 4th link oscillating back and forth. So this is our windshield wiper application. So let's take a peek at a basic mechanism. So on the left is our crank going all the way around, and on the right is the rocker or the oscillating link. Now the total angle that goes through, so if we would measure from here, the angle all the way to the other side. I'm going to kind of bring it back again. That is going to be what we call the throw. Okay. So the crank is over on the left, and then the angle that rocker goes through, just rocking back and forth or oscillating, is going to be the throw angle. And the throw angle is kind of like the stroke of a linear application. So so that's what you're going to be given in the problems that you have for that. And there's going to be one that you'll do in this case. The other one that we have is a windshield wiper. This one's really short, if I remember correctly. Yeah. So look at it one more time, because the beginning is where you can really kind of see the actual mechanism. So that's going to be a crank rocker mechanism, a crank rocker. So as we look here, crank rocker, as we mentioned, the throw angle is going to be that angle between the extreme positions of the rocker length. So if we look at the angular distance between C1 and C2, sorry, always moving different windows around. The crank rocker is going to be up on the top of page 116. So here you'll notice that you have C1 and C2. So those equate to the extreme positions out and in. And then the angle that takes is going to be called our throw. All right. It's going to be called our throw. Here too, the crank rocker can also be arranged so that you can use it as a quick return mechanism as well, but it can also be a symmetrical too. Okay. The radial length between the two extreme positions is going to be 2 times that crank length. Okay. That's going to be a guideline, if you would, that we have for that as well. So procedure for going through this process, you need to locate that pivot position on your rocker. So you start with the output first. What is the throw angle that we're going to be using? Then you start looking at a feasible rocker length. So here too, this is going to be not a number that's going to be given to you. So our rocker again is going to be the oscillating side. So is it 4 inches? Is it 20 millimeters? I don't know. You get to choose. You're the designer. Then you're going to draw it in its extreme positions, about its center of rotation. And then your L2 is going to be 1/2 the AC2 minus the AC1. So those are going to come from this illustration right here. So here's our point A. So this is going to be AC1 and this is going to be AC2. Okay. L3 then is going to be based on, once we get L2, then we're going to take AC1 plus that L2. So it's the same equation that we saw for the offset slider crank. And then you just kind of go through the process and you complete the diagram. Okay. Now, mechanisms that produce the longer coupler rod, the L3, will have lower acceleration. So you try to make that L3 again 3 times or greater than the length of that crank. Okay. Now, transmission angle. The transmission angle is going to be the angle between the coupler and the rocker. Okay, so that's going to be our L3. That's the coupler, and then L4. And we want that to stay as close to 90 degrees as possible. Okay, and not to be outside of 45 and 135. Otherwise, you can get it kind of going over on itself and locking. And that's not a good situation. So we'll see this when we actually lay this out. We'll look at the transmission angle. Okay. All right, so the last part here, we have a couple slides, and these slides are going to pertain to doing some of these problems that you're going to be experiencing for your homework. So the first one we're going to be looking at is going to be problem number 511. And this is end of chapter problem, because they didn't have any examples, which is odd for this book not to have any examples like in the actual chapter itself. So on page 120, we're going to look at problem 511. And the problem statement is directly above. It says for problems 511 through 518, design a slider crank mechanism with a time ratio of Q, which is going to be listed for each one of these. Okay. It's going to give you the stroke, and they use delta R for some reason in this book. I'm not sure why, but that's what they use for stroke. And then the time per cycle in T. Okay, so that's going to be all the way around. Now, it says use either a graphical or analytical method, and then specify the link lengths L2, L3, and an offset L1 if it's going to be applicable. And then also your crank speed. Okay, so for each one of these, we need an L1, L2, L3, and a W, and it would be 2 because it's going to be on our crank or the W of the crank. Now, the first one we're going to be looking at here, you're going to tell me, you'll notice that for 511, and your homework is going to be 512. So it'll be very similar, but different numbers. We have a Q equal to 1. Does that tell us anything? Q equal to 1. I heard it. It's symmetrical, right? So that means that this is a slider crank mechanism, that my outbound speed, my outbound time is going to be equal to my inbound time, right? And my total stroke, my total cycle is going to be 1 rotation around. So they're giving us the total time of our cycle in T. So that's time per cycle. They didn't use their delta in front of here, but they did identify it in the problem statement. Our total cycle time is 1.2. Okay, so if we're going to look at completing this problem, okay, zoom out here a little bit. We want to kind of first identify what we know and what we need to find. So example, I'm sorry, not example, this is problem. Problem 511. We're given Q is equal to 1, so we know that this is an inline, right? I'm gonna call it stroke is equal to 2 inches. Okay, that's what the delta R is. And then our change in T, which is our cycle time, okay, that's going to be 1.2 seconds. Okay. Now, since we know that this is going to be an inline, that means on our equation sheet, we're going to be looking at these 2 equations here to help us determine what our lengths of 2 and 3 are. Okay. And then we're given the stroke. Now, what we need to we need to find L1, L2, L3, and W, we'll call it W2 for the crank, right? Now, L1 is the offset when we have an offset slider crank mechanism. So since this is an inline, what is L1? 0, right? Okay, or not applicable, right? It's not going to be an offset. But now we'll be able to then focus on L2, L3, and W1, or I'm sorry, W2. So what do we want to do first? Knowing we have, kind of these equations here, we know this is our equation for our crank, W2, and then here are kind of where we can start with our distances. You said L2 is 1 inch. Yeah, right, because our stroke is 2 inches, right? Divided by 2, so L2 is going to be 1 inch. So we can say, yeah, we know that L2 is going to be the stroke divided by 2, which we know is 2 inches, divided by 2. So L2 is going to be 1 inch. Okay. So we can put a box around that, but we're going to be using this in AutoCAD to graphically, you know, show this as well. Is there anything else that we can calculate? Yeah, we could do the crank speed as well. So we know what the cycle time is. So we are going to do that one right away too, before we go to CAD. So our W2 is going to be 1 revolution divided by that change in time. And that means that we're 1 revolution per 1.2 seconds. Okay. And then we're going to convert that 60 seconds in 1 minute. Seconds cancel. And our W2 50, yeah. And that's going to be RPMs. Okay. So we've got basically the length of number 2 is going to be 1 inch and 50 RPMs for our W3. Now, is there anything that we can say about W3 or L3? Yeah, it needs, exactly. So we know that this is a relationship we need to maintain, right? Or is ideal. So we're going to say then that number 3, L3 is going to be equal to or greater than 3 times L2. I like writing it that way better. And since we know what L2 is, that means that it is going to be greater than or equal to 3 times 1, which is going to be times 1 inch, which is going to be greater than or equal to 3 inches, right? All right, so now we can start laying this out. So I'm not going to have you guys do this in AutoCAD, but I'm going to show you how I constructed it. Okay, pretty straightforward though. I imagine you can kind of figure it out. So first of all, you'll notice that I drew this in the extreme positions. I started with the stroke first. The stroke was 2 inches. So I had my slider on the right, my slider on the left, the difference between those two on their center. So C2, C3, C1. Okay, A is going to be the center of rotation here. Now, when I have my crank and my connecting rod in line with one another to its outermost extreme position, I know that my L2 had to be 1 inch. Now I have this mislabeled, don't I? Yeah, I do. This dimension should be not from the other side. Sorry. Get it in the right spot. L2, here it is this dimension here. So I'm going to move this. My L2 is the length. It's the radius, not the diameter. So my L2 is 1 inch, which we did figure out, and it's going to be half of what the stroke was. And then my L3 had to just be equal to or greater than 3 times what our L2 was. So 1 times 3 is 3. So I picked 3. Okay. You could pick 4, you could pick 5, you could pick 3 1/4, you could pick 3 1/2. You are the designer, as long as you're meeting that equal to or greater than. Okay. So, so that's the probably the simplest one. The inline slider crank is very straightforward. For your homework, then you would want to use this as your guide. If you would, you want to use your kinematic diagram, standard notation. So number 1 is our frame. Number 2 is our crank. Number 3, connecting rod, and then identify the lengths of each one that you have here, including the stroke. And then you're showing that slider in the 2 positions, with C being the center of the slider. So C1 position, C2 position, the difference between the 2 extremes. Any questions at all? Say that again.
When we submit this, we don't.
You need the CAD.
You do.
Yes, to kind of prove it. Yeah, exactly. No, you do need to do, then it's a screenshot of your result here. Yes. Yeah. So I want you to lay that out. Now this one, analytically, you really can figure everything out, right? We did that beforehand, but on the next ones, it's not going to be that way.
So you only want them on the outside one?
No, I want it here too. Yeah.
Making sure.
You're going to show the graphical solution in AutoCAD for all 3. Yes. Because you're going to have 1 inline, 1 offset, and 1 crank rocker. Okay. All right. Good question. Thank you. All right, and any questions on this? All right, okay. So then let's look at our next example, which is going to be looking at problem 515. Okay, problem 515. All right, so problem 515 is down here, a little bit further down. And you'll notice this time we have a value greater than 1 for Q. So right away, we know that it's not going to be a symmetrical motion, which puts us into the offset slider crank mechanism type, okay? So we have a stroke value of 46 millimeters, and then we have a total cycle time of 3.4 seconds, okay? So we'll start off by kind of looking at, okay, organizing the information we have. So this is problem 515, okay? And our given for this one, okay, is Q is equal to, I think it was 1.37. Our change in time, which is our total cycle time, 3.4 seconds. And our stroke was equal to 46 millimeters. 46 millimeters. So now right away, since we have a value for Q, we're looking at problem 515, Adam, just so you know. This means that this is an offset for us, right? An offset slider crank. Okay. Because it's not 1. Now, what we need to find the same values. So we're going to find L1, L2, L3, and W2. Okay. Now, in this case, we will have an L1 because we are in an offset situation, and the L1 is that distance from the center of rotation of the crank to the path of our slider. Okay. All right. So now, let's go over here and try to figure out what we can actually calculate, okay? So right now, you're gonna notice that we have L2 is equal to, this is the offset slider crank, and the L3 is equal to, all right? Now, do we know, we don't know what L2 is, right? And we don't know what L3 is, so it's kind of hard to do that. So let's see how we can start this process in CAD. Okay. So this was the offset crank that I chose, okay? So I knew that we know that our stroke is 46. So the difference between the out and the in on our slider is 46 millimeters, okay? Now, I wasn't exactly sure what I wanted to use for my offset. So this is one of those things where you pick a number, okay? You just kind of pick a number, and I picked 10 millimeters, all right? And so I did an offset up of 10 millimeters. And then to kind of just make my numbers, you know, kind of relative, if this was 46, I picked a number for my L3 to be 75. So then my crank would be 1/3 of the L3 because I'm still using that same value of equal to or greater than 3 times whatever the crank is. So I just chose 25, or I actually chose 75 first and did 25 for my L2. And then now it's a matter of, well, let's see if this works. Okay. So if you remember, there was a relationship for the length of L1. I don't think I wrote it down. Sorry. My L1 for my offset was, it had to be less than L3 minus L2. So I picked 10, right, for my L1. So when I picked 75 for my connecting rod and 25 for my crank, that is 50, right? So 10 is less than 50. So I'm good, okay? So again, notice that I had to just pick numbers to start in order to kind of go from there, all right? And then as we look here, you're gonna notice that these relationships work out. So what you want to do then is you want to kind of prove your numbers, if you would. So if you measure from C2 to A, and you, sorry, hold on. And we go through this process, you're going to notice that when I want to calculate my L2, and if I take my distance that I measure from AC2 minus AC1 with the values that I have and multiply that by 1/2, it'll come out to 25. Okay. And then the same thing for my L3. Then I'll take 25 plus that number, and that's going to be my 75 millimeters. So it's kind of like what you're going to do is once you get your values and you have it laid out, you're going to measure your AC1s and your AC2s, and you're going to then prove that your radius is what it's, or your crank length is what it's supposed to be. Okay. And then the same thing back for the L3, and make sure that that number works. And then again, I'm going to add this to my equation sheet that my L1 is less than the length of 3 minus the length of 2. So my L1 has to be less than, let's see, L3 minus L2. Okay. And I know it doesn't feel very concrete. So some students are like, well, where do I start? And it's literally, you would know more about your application. In the real world, you would have an idea like the envelope that you want this to fit into. And then it does become easier when you have those variables. Sometimes it's like, you almost have too much freedom. It feels weird, you know, just picking a number, but for those, you really do. And then you kind of go on, you then check them to the math. Okay. So for this one, when you lay this out, kind of that same thing, you're going to want to go through and you're going to want to put your values in place here. Now, for this one, it doesn't ask for it, but notice we do have a beta because this is offset. When we're in our outermost position to our innermost position, there is an angle between there. Okay. And that's that imbalance angle. I encourage you to check it and see what you come up with. Okay. For your design, using that Q. Okay. And you should get the same value that you have on the Q there. Okay. Any questions? Oh, I know what I didn't do. We didn't do our W for this one, did we? Let's see. We didn't do our W yet. So we did you can figure out your lengths again by drawing them out and then making sure that they abide by, oopsie, I have the wrong one here. Hold on. Abide by the rules. So we picked L1, I picked 10 millimeters. My L2 was 25 millimeters. I had 75 millimeters. And then now I just need to calculate my W2. My W2 is going to be 1 revolution divided by my change in time for my cycle. So it's going to be 1 revolution divided by 3.4 seconds. Okay. And that number would be 0.2941 revolutions per second. And then we're going to convert that to RPMs. Okay. And then our W2 is going to be 17.65 RPMs. Okay. Any questions? All right. Now, the last problem that we have is going to be problem number 519. And this is a crank rocker mechanism. Now, for this one, we need to specify the same values that we had. So let's look at what we've got here. Okay. The end of the chapter. So this one is 520. Okay. Now for 520, we want to find still L1, L2, L3, and L4, and then that crank speed, okay? Now, they're giving us a Q is equal to 1. So what that means is when we look at the throw angle, it's going to be half of the total throw in one direction and the other half in the other, which means that your time is going to be even on both sides. Okay, so we're going to have a Q equals to 1. It's going to be a symmetrical. And then you're going to see that they are giving you a 78-degree throw angle and our time is 1.2. So that means half is 0.6 in one direction, half in the other. Okay. And then for this one, an L1 for a crank rocker is not an offset. It is the distance. If we look at page 116, it's the distance between, the straight line distance between here. These can be in line like this, or they can be offset. But if they're in line, then the L1 is the distance between the two. Okay. And again, that's another value that you get to pick, So if I go back to my AutoCAD here, when we set this one up, where you start is going to be on your throw angle. Okay. So the 78 degrees. So going straight up and then dividing that by 2. So 39 in one direction, 39 in the other. Okay. And once you position that, now you need to determine the length of link number 4. Okay, so how long is link number 4 going to be? I picked out of the air 4 inches. That's what I did. All right, I picked that number out of the air. It wasn't given to me. I just kind of looked at it like, okay, I literally drew my line along that angle, and I'm like, it's about 4. So I keyed in 4. That was it. Okay. Again, in the real world, you would have some space that you would have to fit within. Okay. And then I knew that I wanted my value in between here to be, I wanted these two to be in line with one another. So this came out to be 6 inches. All right. And then you're going to notice that as I placed that, I went in my extreme position this way. And what ended up happening was I had to calculate using my values 9.067, which is my A to C2. And then I had to find my length. This is 4 inches again of A to C1. That's the 4.668. And I use that in the equation, which is the same for the offset. So for L2, it's going to be 1/2 times A times C2 minus A times C1. So using those two distances from over here, oopsie, I grabbed the wrong one. The 9.067 minus the 4.668, multiplying that by 1/2, subtracting those two, that came out to be the length of my L2 here. I think it was 1.995, and I did put it in, but I have 3 decimal places, so it rounded for me. So I'm sorry, 2.1995 was the number. The distance between, that's going to be the length of my crank. That's my L2. Did you say AC what?
Yeah. AC1 is the distance between A and C.
Yep, A and C1, correct. Yep, and that's the 4.668. Yep, and then my A to C2 was the 9.667. Yeah. And then you just make sure that those numbers come out. You use those values. And so the first two that I needed to set up my 78 first. I needed to pick a length out of the air of my link number 4. And then I just needed to determine how far apart did I want these. Okay. And again, picked a number. That was it. And then that set up the geometry for where A was going to be. And then the numbers that I had to then grab to determine the length of number 2. And then L3 is just going to be the difference between those two, right? I didn't put that, I didn't put that dimension on here, but that would be one that you'd also have to, and you can graphically get it and then prove it. With the numbers. Oops, I needed an aligned dimension. Okay, so then you want to just make sure that those numbers all come out, and they will. It's very straightforward. Graphically doing these, yes. Because really you need to graphically do them before, because you need this number and you need that number to get your crank length. And then once you get the crank length, then it's going to be the difference, you know, between the two. Yeah. So that's the third problem that you have. Okay. So so let's take a look. You are now ready. If we look at our PowerPoint presentation, you'll notice that the last one says it's a wrap. You now are ready to work to complete all of the homework. So let's take a look at the homework assignment. Oopsie. Too many things down here. Here's my, so I'm going to go back to module number 8. I'm going to go to assignment number 8. And at the end there, we've got 5254. These are 10-point problems. These are going to mimic those relationships between beta, Q, cycle time, and the angular velocity. So let's take a look at those 2 and 5. Okay. So on page 120, 5.2 is your homework problem. Okay. And here it says you want to determine the time ratio. So that's going to be Q, the imbalance angle, beta, and the speed at which the mechanism should be driven. So that's going to be your W of your crank. Okay. They're giving you time 1. So that's going to be the time in the outward stroke. And then time 2 is going to be the inward or the return. All right. So from those two numbers right there, Q, beta, and W. All right. Then for problem number 5, they're giving you a little bit different information. This time you want to determine Q, your time 1 and your time 2 with the information you get here. So you've got a beta angle and you've got a W. Okay. Then the next problem that you have is going to be problem number 12. That's going to mimic the example 511 that we looked at. That's going to be an inline crank because it's got a Q equal to 1. Okay. And then you're going to have an offset crank, which is going to be 516 because that's got a Q of 1.15. And then lastly, you've got a crank rocker, number 20. It's got a Q1, so it's evenly distributed, half of that throw angle on either side to mimic that last problem that we just looked at. Okay. So any questions right now? So graphical for the last 3 with the work that you need to kind of get things started and going. And then for the first 2 here, 2 and 4, that's just calculations, no graphical solution for those. All right. So as far as due date, this is going to be due then on the very last day of our class, which is December 15th. And then you have until midnight and, to do that. So I'll talk a little bit about calendar after I get done with the recording here. So I'm going to stop the recording unless there's any other questions as you're looking. Okay.